Imagine standing on the edge of the Mediterranean Sea 2,000 years ago, watching Roman engineers pour a strange mixture into wooden forms submerged beneath the waves. And if you asked them what they were doing, they would tell you they were building a harbor that would outlast empires. And they were right, because today, 2 millennia later, those same concrete structures still stand beneath the churning waters, while our modern concrete crumbles after mere decades. And this is not a poetic exaggeration, but a scientific fact that has baffled engineers for centuries, until recent breakthroughs revealed a truth that should humble every modern materials scientist. The Romans didn't just build concrete, they engineered a self-healing material that actually grows stronger with time. A feat we still cannot fully replicate, despite all our advanced technology, supercomputers, and billion-dollar research budgets. The story begins with a crisis, as all great engineering stories do, because around 30 BCE, Rome faced a problem that threatened its very survival as a Mediterranean power. They needed to build massive harbor infrastructure to support their growing naval and commercial fleets, but the conventional building materials of the era, cut stone, fired brick, timber, simply could not withstand the relentless assault of salt water, the pounding of waves, and the corrosive marine environment that would reduce even the finest masonry to rubble within a generation. The engineers of Rome, whom we have foolishly dismissed as ancient, as if that word implies primitive, looked at this challenge not with resignation but with the systematic curiosity of true scientists. And they began experimenting with a volcanic ash from the region of Pozzuoli near Mount Vesuvius, a material the locals called pulvis puteolanus, which we now call pozzolanic ash. And when they mixed this ash with lime and seawater, yes, seawater, the very substance that destroys modern concrete, something miraculous happened at the molecular level that they could not see but could certainly observe in the remarkable durability of their structures. Modern science has only recently unlocked the secret of what those Roman engineers discovered through empirical experimentation over 2,000 years ago, and the findings, published in journals like American Mineralogist and examined through X-ray fluorescence spectroscopy, X-ray microdiffraction analysis, and scanning electron microscopy at facilities including the Advanced Light Source at Lawrence Berkeley National Laboratory, reveal a material so sophisticated that it challenges our fundamental assumptions about ancient technological capability. When researchers led by geologist Marie Jackson analyzed samples of Roman marine concrete drilled from ancient harbors at Portus Cosanus, Baiae, and other sites, they discovered something that seemed to violate everything we know about concrete degradation. Instead of calcium silicate hydrate compounds that characterize modern Portland cement and gradually weaken when exposed to seawater, the Roman concrete contained a night mineral called philipsite, growing in interlocking crystalline structures throughout the material. And most remarkably, these crystals were not present in the original mixture, but had grown over centuries of seawater exposure, meaning the concrete was literally healing itself and becoming stronger through the very environmental exposure that destroys modern materials. The specific chemistry involves the volcanic ash, which contains aluminous tobermorite and philipsite crystallizing in the calcium aluminum silicate hydrate binder. And when seawater percolates through tiny cracks in the concrete, cracks that would be death sentences for modern structures, it triggers a pozzolanic reaction that precipitates new mineral growth, filling the cracks and actually reinforcing the material. And this process has been continuing for 2,000 years, which is why ancient Roman breakwaters remain solid, while modern marine concrete structures require constant maintenance and replacement after 50 to 100 years at most. Let me give you the numbers that should make every modern engineer pause in humility. Modern Portland cement concrete, the material upon which our entire civilization's infrastructure depends, typically has a functional lifespan of 50 to 100 years in marine environments before requiring significant repair or replacement. And the global concrete industry produces approximately 4.4 billion metric tons of cement annually, accounting for roughly 8% of global carbon dioxide emissions, more than the entire aviation industry. partly because structures must be constantly rebuilt. Roman marine concrete, by contrast, has demonstrated structural integrity exceeding 2,000 years, and samples tested in modern laboratories show compressive strength values ranging from 7.5 to 10.5 megapascals, which, while lower than modern high-performance concrete's 30 to 50 megapascals, represents a material that achieves this strength without the massive carbon footprint of modern cement production and actually improves rather than degrades over time. The thermal analysis reveals that Roman concrete production required heating limestone to only about 900 degrees Celsius to produce quicklime, compared to the 1,450 degrees Celsius required for modern Portland cement clinker, representing a roughly 40% reduction in energy requirements at the most energy-intensive step of production. And when you multiply this across the billions of tons of concrete humanity produces annually, the implications for addressing climate change become staggeringly clear. But the Romans were not merely lucky, they were systematic. And the evidence suggests a sophisticated understanding of materials science that we have only recently begun to appreciate. The recipe recorded by Vitruvius in his 1st century BCE treatise De Architectura specifies precise ratios: 1 part lime to 2 parts pozzolanic ash for marine applications, with the volcanic ash specifically sourced from regions around the Bay of Naples, where the unique geochemistry of ancient eruptions produced tephra with optimal aluminum and silica content for the pozzolanic reaction. Modern X-ray fluorescence analysis of ash samples from Roman concrete shows silicon dioxide content of approximately 55%, aluminum oxide at 18%, and iron oxide at 8%, with trace amounts of calcium, magnesium, potassium, and sodium that together create the ideal conditions for long-term mineral crystallization in marine environments. The Romans understood, through centuries of accumulated empirical knowledge passed down through guilds of specialized craftsmen, that not all volcanic ash was equal. Ash from Vesuvius produced superior marine concrete compared to material from other volcanic regions. And this knowledge, though expressed in practical rather than chemical terms, represents genuine materials science. Thermal imaging of standing Roman structures reveals another dimension of their engineering sophistication. The specific density and porosity of Roman concrete creates thermal mass characteristics that moderate temperature fluctuations, with structures showing temperature differentials of only 5 to 8 degrees Celsius between day and night cycles, compared to 15 to 20 degrees for modern concrete, reducing thermal stress that causes cracking and extending structural lifespan. The tragedy of history is that this knowledge was not truly lost, but deliberately abandoned, and understanding why reveals as much about human nature as about engineering. When the Roman Empire collapsed and the infrastructure of knowledge transmission, the engineering guilds, the trade networks that supplied specialized volcanic ash, the institutional memory of large-scale construction projects, fragmented, the specific recipe for marine concrete became just another casualty of civilizational decline, and medieval builders, though capable of remarkable achievements in their own right, worked with different materials and different priorities. When modern cement was developed in 1824 by Joseph Aston, who patented what he called Portland cement because it resembled the prestigious Portland stone when set, engineers were solving for different variables than their Roman predecessors: rapid setting time, high early strength, and ease of manufacture from widely available limestone, rather than geographically specific volcanic ash. These priorities made perfect sense for the industrial age, when speed and scalability mattered more than multi-century durability, but they locked our civilization into a materials paradigm that we are only now recognizing as fundamentally unsustainable. Every year, approximately 30 billion metric tons of concrete are poured globally, requiring the quarrying, transportation, and processing of staggering quantities of raw materials, the emission of roughly 2.8 billion metric tons of carbon dioxide, and the certain knowledge that most of these structures will require major renovation or complete replacement within a few generations. The modern research inspired by Roman concrete is not mere historical curiosity, but a desperate search for solutions to existential challenges. At universities and research institutions across the world, scientists are now attempting to reverse engineer the Roman recipe for contemporary applications, and the results are promising but humbling. Researchers at the University of Utah have developed a concrete mixture incorporating volcanic ash that shows self-healing properties similar to Roman marine concrete, with crack-filling efficiency of up to 75% in laboratory conditions. Teams at MIT and Stanford have used computational fluid dynamics modeling to understand how the microstructure of Roman concrete affects the flow of seawater through the material, identifying the specific pore geometries that optimize mineral precipitation without compromising structural integrity. The European Union's Seawater Project has invested millions of euros in developing modern equivalents of Roman pozzolanic concrete for offshore wind turbine foundations, where current steel and conventional concrete structures face maintenance costs exceeding 25% of total project lifetime expenses due to marine degradation. These efforts matter because our coastal infrastructure faces accelerating threats. Sea level rise of 0.3 to 1.0 meters projected by 2100, increased storm intensity, and the steady deterioration of concrete structures built during the 20th century's infrastructure boom all demand materials that can endure for centuries, not decades. Consider the human dimension of what the Romans achieved, because engineering is never merely technical, but always social. The construction of major Roman harbor works like those at Caesarea Maritima, built by Herod the Great using Roman techniques around 25 to 13 BCE, required the coordinated labor of thousands of workers over more than a decade. The establishment of supply chains extending hundreds of kilometers to source the specific volcanic ash from Italy. The training of specialized craftsmen in the precise mixing and placement techniques that determined whether the concrete would achieve its remarkable durability or fail like ordinary morite, and the institutional commitment to projects whose benefits would not be fully realized for generations. This represents a form of intergenerational thinking that our modern, quarterly, profit-driven civilization struggles to sustain. The engineers who designed these harbors knew they were building for their grandchildren's grandchildren, and they designed accordingly. The archaeological evidence shows that Roman construction projects often employed disabled workers in roles suited to their capabilities. That engineering knowledge was preserved and transmitted through formal apprenticeship systems lasting 7 to 10 years, and that successful completion of major infrastructure projects was celebrated as civic achievement benefiting the entire community rather than merely private profit. There is a moral architecture underlying the physical architecture, a recognition that great works require great cooperation and that building for eternity requires thinking beyond individual lifespans. The implications for our current moment extend far beyond concrete, because what the Romans demonstrate is not merely a superior building material, but a superior approach to technological development. Modern engineering tends toward complexity, specialization, and dependence on fossil fuels and rare materials. Our buildings require continuous energy input for heating and cooling. Our infrastructure demands constant maintenance. Our materials are designed for planned obsolescence rather than permanent endurance. Roman engineering, operating within severe constraints on available materials and energy, developed solutions that worked with natural processes rather than against them, that improved rather than degraded over time, that required minimal maintenance once installed. This is not romantic primitivism, but hard engineering logic. A structure that heals itself using freely available seawater is objectively superior to one requiring constant intervention with manufactured materials. A harbor that has survived 2,000 years of Mediterranean storms, earthquakes, and human conflict represents a design philosophy that we would be wise to study and emulate. The scientific analysis of Roman concrete is thus not merely archaeology, but research and development, a recovery of lost intellectual property that could help solve some of our most pressing environmental and infrastructure challenges. So the next time you hear someone use the word ancient as a synonym for primitive, remember those Roman engineers standing on the shores of the Mediterranean, mixing volcanic ash with lime and seawater according to recipes refined over generations, building harbors they knew would outlast their empire. And ask yourself, who are the real primitives here? We who build disposable structures that poison our atmosphere, or they who built self-healing materials that grow stronger with each passing century? The evidence, analyzed through X-ray fluorescence and electron microscopy and computational fluid dynamics, suggests an answer we might find uncomfortable but cannot honestly deny. The Romans were not crude precursors to our sophisticated age, but masters of a materials science we still struggle to understand, and their concrete, still standing after 2 millennia beneath the waves, offers not just a technical lesson, but a philosophical challenge. Can we learn to build for permanence rather than profit, for generations rather than quarters, for a future we will never see but can choose to serve? The harbor at Caesarea still stands. The breakwaters at Portus Cassanus still defy the sea, and somewhere in that volcanic ash, transformed by seawater and time into interlocking crystals of eternal stone, there is a message from engineers who have been dead for 2,000 years, a message that modern science is only now learning to read. We knew something you have forgotten, and if you are wise, you will remember.